Hello, my name is Peter Ansdale, and this is my presentation on Lab 3 of Physics 1 at Georgia Tech on black holes and orbits. So here's an introduction to the first part, which is focused on the orbit around a black hole. The purpose of this part is to use a computational model to find the mass of the given black hole. And the models / fundamental physical principles used in this lab are the momentum principle, otherwise known as Newton's second law, and the force of gravity for universal gravitation. The model we're using is GlowScript, and the preview result is that I got the mass of the black hole to be 8.27 times 10 to the 33 kilograms. Here are the main physics ideas used in both parts 1 and part 2 of this lab. A lot of these are familiar, such as Newton's second law, which turns into the momentum update formula, which then turns into the velocity update formula, which you can use for the position update formula. But the key physics ideas for this lab are the force of gravity for universal gravitation, negative g big N little m over the magnitude of r squared times r hat. And then the parallel and perpendicular components of Newton's second law. Pretty self-explanatory there. And here's the actual lab for the first part itself. As you can see, the initial conditions we have here are the gravitational constant, the mass of the star, which is a given, and then the time interval, which is the number of seconds in one day. And then for the lab, you can see that we are using the momentum principle here to find dt, and then we use our given information to find dp dt parallel and dp dt perpendicular. And we basically reverse the force of gravity equation to solve for the mass of the black hole, which you can see is done here. And this is, in this experiment, the system is a star and the surroundings is the black hole. Or you could look at it the other way. You could look at the black hole as a system and the surroundings as a star. It'll give you the same force of gravity based on reciprocity. So here's the results. So here's the sum of all results was this number right here. There's way more iterations, but I just showed the last few here on the screenshot. There are 460 total. So you divide that and you get 8.27 times 10 to the 33 kilograms. So per Newton's second law, the net force and the rate of change of momentum are essentially the same. However, observationally, the net force is an instantaneous measurement, while the rate of change of momentum is a measurement of momentum over time. So here's the second part. The purpose: we're trying to successfully orbit a spaceship around a stationary planet and a moon, which is in circular orbit around the planet, so that the spaceship moves in a figure 8-like path without crashing into either the planet or the moon, and determine what initial velocity the spaceship had to have to successfully accomplish this. So once again, we're using the same models / fundamental physical principles as part 1. Here's a preview of the result, the initial velocity. Let's look into this a little bit farther. So in this experiment, the system is objectively defined as a spaceship, while the surroundings are the planet and its moon. So here are the initial conditions. After many iterations of trial and error, I determined the velocity for the ship initially to be these components, and then we use a plethora of formulas here. We use a momentum update, velocity update, position update, and then you're adding the different components of the forces for each thing. So on the planet, on the moon, on the ship. Eventually, that gets us to determine the initial velocity of the spaceship to be negative 1.85 times 10 to the 4th in the x direction and positive 3.5 times 10 to the 4th in the y direction, meters per second. And this is the path that it took based on my calculations and code. So you can see it obviously was not a perfect figure 8, but it never crashed into the moon or the planet. So it was a successful path. And what if, for the hypothetical, You also need to take into consideration the black hole as a part of the surroundings, in addition to the original surroundings. And the black hole will be the dominant source because it has such a large mass. And that's it. Thank you for watching.